So we're doing heteronuclear diatomics, and these all have the point group of C infinity V. So we've gotten rid of the inversion center because we have two different atoms. And this changes all of the symmetries. We no longer have G and U symmetry because we don't have that inversion center. So these are just A1, A2, E1, E2, E3, E4, E5, all the way to E infinity. Okay, so there's just A1 and 2 are the single dimension symmetries, and then anything that's in the X or Y direction is going to be coupled together, like X and Y are indistinguishable, so that's two-dimensional. Once we get beyond E2, then there really aren't any Cartesian combinations that give us those other ones that are at least first or second order. So all we really need to know are the first 4 rows in this character table. And so we see that Z and Z squared are up here at the top. That would be A1. X and Y would be E1, and so would be XZ and YZ, and we'll see those, the importance of those also. So it's going to be a lot of A1s and E1s. So S orbitals, PZ orbitals, sigma and sigma star orbitals are going to be at top row. They're going to be A1. And that's really very nice. It's very convenient to know that anything that has that sigma symmetry, sigma star, or S orbitals, or anything along the Z axis, PZ orbital, or like the DZ squared orbital, Z squared minus X squared minus Y squared is going to be A1. Anything with the X or Y, like PX or PY, would be E1. Any pi bonding, so pi bonding has a X character or Y character, and that's going to be E1. And then the DXZ and DYZ orbitals will be E1. You have the X squared minus Y squared D orbital, that would be E2, and the DXY orbital would also be E2. And so then also those pi star orbitals are going to have this character, the XZ character and YZ character. So we'll see pictures of all of these today. So let's make HF, one of the simplest heteronuclear diatomics. The very first thing we do in a molecular orbital diagram is draw the atomic orbitals. So we put an atom on each side. It doesn't matter if H is on the left or H is on the right. And the upmost or the highest energy atomic orbitals are going to be close to each other. Now, I don't know if H is above or below the p orbitals on fluorine, if I were to sit down and do this problem, okay? But they're not, I mean, chances are they're not equal. So you might just put one a little bit above the other. Now, if I had to put H below this one, it would still be right. You know, what we would have to do to judge that would be to go to some sort of computational package or some experimental result. So we really wouldn't know if the hydrogen was above, the H1s was above the fluorine, but you know that hydrogen orbital has the energy it has because of the nucleus, and it only has 1 proton, whereas fluorine has how many over here? 9. So it's going to be pulling those orbitals down. So it makes sense that the fluorine orbitals are a little bit lower than the H1s. But that's your first guess, is to say, okay, where are these orbitals relative to each other? And so are they have any questions about that? So you've got the atomic orbitals here. Now you might want to also put the electrons in there. So fluorine having 7 valence electrons, you put 1, 2, 3, 4, 5, 6, 7. So we'd have 7 electrons in the fluorine side and 1 electron in the hydrogen side. And so then you can label the symmetries of those. And so you have the S orbitals are A1 symmetry from the character table before. The PZ orbital is A1 symmetry, and the PX and the PY are E1 symmetry. So we have all of those, and you can be drawing this diagram in your notes if you want to reinforce it to learn how to do it. So I'll go slow enough so that you can stay with me and draw this. So have a whole page dedicated to this MO diagram. Now, I really don't like the way the book draws these p orbitals. I like to draw them split out. So I do this so I can show the electrons in these orbitals, you know, as opposed to 3 on top of each other. But it seems like all the images that I have that are from the book have 3 lines drawn on top of each other like that. I like to split them apart. personal preference. So then we look at the symmetries of the atomic orbitals, and only those things that have the same symmetry will mix. That's a principle, the symmetry principle, that only things of A1 symmetry are going to be able to mix with other things of A1 symmetry. So the E1s, the E energy levels have nothing to mix with. So right away we know that the PX and the PY are just going to come straight over and not mix with the hydrogen at all. Because if you think about a p orbital and an s orbital, the p orbital might have the same sign on one side but the opposite sign on the other side. And so whatever benefit you get by mixing with an s orbital and a p orbital, you lose at the other side of that p orbital. So the net overlap is going to be 0 between a p orbital and an s orbital. And so we mix together the A1s here in a bonding or an in-phase arrangement. And these are so far away in energy that there's really very little interaction. You see, this energy level doesn't dip very much at all because they're so far away in energy. Whereas the PZ orbital is going to mix very well with this hydrogen 1s because they're close in energy. And so that's this very little bit of mixing is shown here in that the amount of 1s character that plays into this molecular orbital versus the amount of 2s that plays into this orbital. The 2s, it's mostly the 2s orbital. You see, just the relative sizes. They're trying to show that this is mostly the 2s on the fluorine. So then we have the PZ mixing together with the 1s. And now you see the 1s interacting with this side of the PZ orbital. You have a node on the fluorine atom, and you have the negative side of that PZ orbital on the other side. So we have a molecular orbital down here with 0 nodes. We have a molecular orbital with 1 node. And then up at the top, you're going to have the molecular orbital with 2 nodes. So there's a node here that breaks the bond. So that would be an antibonding orbital. Now these are using p orbitals, but does that mean it's a pi bond then, if it's using a p orbital? No, it's not. It's end-on interaction, and so it has rotational symmetry around that bond, so it's going to be a sigma interaction. So that's a sigma and a sigma star bond and antibond. And those are all A1, because those are A1 orbitals mixing with A1 orbitals. Now we started, and this is, everybody pay attention to this statement, we started with 3 atomic orbitals, and we generated 3 molecular orbitals. Okay. So the number and types of orbitals or the number of orbitals are conserved. And then we have the PX and PY orbitals on the fluorine that just come straight over as non-bonding. So the non-bonding PX and the non-bonding PY. And so the pictures for those are essentially, there's no interaction with the hydrogen, so it's just the PX and the PY orbitals on the fluorine. So this is a heteronuclear MO diagram of a 1s, a hydrogen, interacting with a second row element, fluorine. What would be different if I made this HCl, if I made it chlorine instead of fluorine? What's that?
Maybe the level of entities?
The levels might shift a little bit, yeah.
Could it be very similar?
Be very similar. So very little changes. There is only really one thing that will change, or 2 things, 2 labels on here that will change. Yeah.
The number of electrons and orbitals?
Well, we're dealing with valence electrons, so even that doesn't change. So we still have all the core electrons down below. Notice we didn't draw the 1s orbital on the fluorine. It's down below the floor somewhere.
Maybe 3p?
Yeah, 3p and 3s. That's the only change. So HBr, 4p, 4s. So once you learn one, you've learned a lot. Okay. So you learn HF, you now know HCl and HBr. You just change the 2s to 3s and the 2p to 3p, and you've got HCl. Same pictures, same number of electrons because we're dealing with valence electrons. and the core electrons are not shown. Tell you, every year I have somebody, when I ask on the exam, some third row element like HCl, they have like the 2s and the 2p's and the 3s and the 3p's, and the diagram's so incredibly complex because they haven't really realized that, no, it's just the valence electrons that are bonding. The core is complete and it's buried. It's so close to that strongly positive nucleus that it doesn't participate in bonding. So only the valence shell is participating in bonding, and that's why we have group character. That's why chlorine acts like fluorine, because it's just those 7 electrons that are in that outer shell that are interacting. You don't even know that those other electrons are there in the chlorine. And then we put in the electrons in the middle, so we have 8 electrons, and you start from the bottom, 2, 4, 6, 8, everything's all paired up. Now the labeling, and this is, notice how this, I showed some interaction with the H1S, but it was very little interaction. So that's essentially like a non-bonded interaction. So those 2 electrons, you could call that a sigma interaction, or you could call it, since it's so close to the 2s, this is where it really becomes ambiguous. It's like, is it a sigma? Is it a non-bonding thing? If I call it a sigma, then I end up with a bond order of 2 for HF. And it's really more characterized by a single bond. The bond length is a single bond, the bond strength is a single bond. So labeling this as a sigma would give me 2 sigma bonds in HF, when it's really just 1. If you look at the experimental evidence, it's just a single bond. And so that really gives support to this just being non-bonded. So really the 2s electrons aren't really interacting strongly with the 1s electron and hydrogen. Does that make sense? And then the p orbitals are coming across. They have nothing to bond with because their p nature doesn't bond with an s orbital. Okay, so those are non-bonded. So when we add up the bonding electrons, we have 2. Antibonding, we have 0. We divide by 2, we get 1 for the bond order. Thoughts, reactions? If you were to do this by yourself, where would you get stuck?
Probably at the PXPY.
Okay, just thinking about them, what are they going to bond with? Yeah, if they have nothing to bond with, then they just come straight across and they become non-bonding.
Can you repeat how you figured out the bond order?
That's a tricky thing, because if I was looking at this as a sigma bond, then when I add up the bonding electrons, I'd have 4. And I look at the antibonding electrons, I'd have 0. And so it's number of bonding minus antibonding divided by 2. So I'd have 4 minus 0 divided by 2, and I'd get 2 bonds. But I look at HF and I think, yeah, really, I'm not sure. I'm not convinced it has 2 bonds. It's not a double bond to the hydrogen. Okay. And so that would make me think that this 2s is so far away from the 1s that it's probably just non-bonding. It's probably just coming across as it. So those electrons are essentially staying on the fluorine. They're not moving over the whole molecule. They're just stuck there with all those protons. But the PZ, those electrons are ranging over the whole molecule and making that single bond. Because remember, we're talking about molecular orbitals. If it's non-bonding, it's really just stuck on an atom. If it's molecular, if it's bonding, it kind of smears over the whole molecule. Or if it's antibonding, it also jumps over the whole molecule. So let's look at this. If this, so there's the bond order calculation. And so the non-bonding electrons don't figure into this calculation because they don't impact the bonding.
So would it be a safe assumption to say typically hydrogen will stay towards the outer shell, outermost of the valence, instead of bonding to, let's say, an s orbital on something else?
Yeah, that's, it's going to be interacting with the p orbitals. Yeah, I'm trying to think. It's going to be, it's the highest energy atomic orbital that hydrogen has, and it's going to interact with the highest energy atomic orbitals that the other elements have, and those are going to either be p orbitals or d orbitals. It can interact with d orbitals. Yes.
So should we draw like Lewis
dot structures with this to determine like how many sigma you would have, because if you declared like the bottom one is sigma, you couldn't have like 6
Yeah.
electrons on.
Right, yeah, and so you'd have a hydrogen with 4 electrons, you know, nearby, and that would be also problematic. Yeah. And so we'll see when we get to carbon monoxide, this sort of looking at the Lewis dot structures and looking at the MO diagrams, and there's some tension there. It's really kind of ugly. Remember, Lewis dot structures are most closely tied to local bond theory. And so tying them to molecular orbital theory, like carbon example, would be a quadruple bond. And so it's not supported by MO theory. Yeah. And so then we looked at this. Let's see if we, you know, the experimental results do tell us that this is an accurate picture. So if we have the ionization limit and we hit this with light, we can knock electrons out of atoms like fluorine and hydrogen, and we can knock electrons out of the molecule. And so if we look at this, the fluorine 2p orbitals are around 18.6 electron volts. The hydrogen 1s is 13.6 electron volts, so it's higher in energy. Okay, so we're looking at the amount of energy it takes to get to the ionization limit. So it's a smaller number, which means it's higher in energy. But if you follow that, sort of the depth of those orbitals below the ionization energy is what we're measuring. And then we have the bonding, 18.8. It's pretty close to the fluorine. It's not much of a drop. And then the non-bonding is 18.6. And then up there at the top, that antibonding is 13.4. How would we measure that if there were no electrons in there? Well, we could make an anion and sort of calculate what energy would give that. Or we could also look at what they call shake-up states, where you have electrons, like one electron comes out with a little bit less energy because another electron jumped to an antibonding orbital. So there's some other funny phenomena that happen with X-ray and UV photoelectron spectroscopy that allows us to get other energy levels in their information. So we get all of this data from UV photoelectron spectroscopy, and then that's really how we correct our MO diagrams to make them accurate. But I'm just going to be testing you on, can you get the general structure of the MO diagram? I'm not going to test, oh, you put hydrogen below 2p, -5, you know. But I'm going to say, you know, you got the hydrogen orbitals and the p orbitals on there, you put the electrons and everything, you labeled the symmetries. Your homework and your test results should look just like this. Everything, all the symmetry labeled. I'm going to ask you to draw some pictures. So you should be able to do this whole thing. Because if you can do this, you can understand bonding. And if you go into the field where you need to think about bonding, this is going to be one of the tools that you need to use. Now, one thing that's not labeled on here is, where is the highest occupied molecular orbital? So first off, the molecular orbitals are in the middle. Okay.
Be that sigma.
And so remember, the molecular orbitals are in the middle, so even the non-bonding orbitals are molecular orbitals. Okay, they're just not bonding or antibonding, they're non-bonding. But they qualify. They're in the middle, so they qualify as a molecular orbital. So these non-bonded orbitals on the fluorine are the highest occupied molecular orbitals. So that's the HOMO, is the highest occupied molecular orbital is the non-bonding orbitals on the fluorine. So that's what HOMO stands for, highest occupied molecular orbital. And that's a vocabulary word in your homework that I just posted this morning. And then where's the LUMO? The lowest unoccupied molecular orbital. That's up here at the top. Yeah, so that's that sigma star. So you should be able to label the HOMO to LUMO, HOMO and LUMO, and you should be able to figure out the symmetries of the HOMO to LUMO transitions. Right? So just like we used the transition dipole moment, we could figure out what kind of light would cause this transition. And so in that situation, we'll do this on the board. So we have X or Y, which is E1, and Z, which is A1.
Yeah.
And then the LUMO light and the HOMO. So this would be the transition dipole moment that you would set up. And so then you just had the symmetries of all of those. The highest occupied molecular orbital were those non-bonded pairs, right? So that was E1. Okay. And then the lowest unoccupied molecular orbital was the sigma star, so that's A1. And then light, what are we going to, I mean, you've done enough of these now that you've got two choices, A1 or E1. And here's what we've got. So what is going to go in here that's going to help us? E1, because anything times itself is going to contain A1. Okay? So E1, so that would be XY light. So E1 times E1 is going to be at least A1 plus some other stuff. I don't even need the direct product table. It's going to contain A1, which is then when you multiply by A1, it's going to be A1. And that's not equal to 0, so this is allowed. Okay. So that's a fantastic tool to know. Now that I've got the molecular orbital diagram, I can analyze it because I have the symmetries, and I can determine the selection rules for HF. That's pretty cool. So I can just start with the atoms, bond them together, make the molecular orbitals. I know what mixed to make the molecular orbitals, and now I know the properties of interaction with light. That's what this whole course is about, is light interacting with matter. So we're learning about the bonding, but then after we've done the molecular orbital diagram, we can analyze it to see how light will interact with this molecule. And so the data from the UVPS supports the molecular orbital theory of the structure of the electron cloud. Remember, this is what we're talking about, is the shapes, that's the structure of the electron cloud. Now let's get into a little more interesting one. This is carbon monoxide. And so if I did this with myself, and if I'm going to do a molecular orbital diagram and I'm sitting in front of my computer, I'm going to do a Gaussian calculation on the atomic orbitals and on the molecular orbitals so I can get accurate or somewhat accurate energies. Okay, and so this isn't anything that you would be able to do by hand necessarily, just getting accurate energies. But putting that aside, you could still do this molecular orbital diagram by hand. But I wanted to show you, as at least according to Gaussian, an accurate view of the molecular orbital diagram. So one thing that you can do to calculate the energies of the atomic orbitals is this keyword in Gaussian called pop equals full. So population, you're asking it to calculate the population of the energy levels, and you want all of them. So full, it just tells you calculate the population of all the energy levels, and it's going to give you their energies. And then you can calculate the molecular orbital, the molecular energies, doing an opt-in-free. Y'all are familiar with that calculation, but also including this keyword, pop equals full, will give you the occupation and the energies of all of those molecular orbitals. And so here's the output. So we see here for, let's see which one this is. This is for carbon. We have minus 10 Hartrees, and then minus 0.5, and then 0.25, 0.25, and 0.13. So we've got 1, 2, 3, 4, 5 occupied orbitals. We have a lot that have positive numbers, and so those are the unoccupied orbitals. And when you give it all of these basis functions, you're giving it d orbitals, all kinds of extra orbitals. And if they're not populated, they're still calculated. Those energies are calculated, but there's just no electrons in those d orbitals. But their presence allows them to mix in at like 0.1% to stabilize the energies and make them better. So that's always a good practice to give Gaussian more freedom for the electrons. But in the end, you still get the same populated orbitals that you would get if you used a minimal basis set. So the minus 10, what is that? That energy is the energy of the 1s orbital, okay? And then the minus 0.5, what's the next orbital? 2s. And then these last three are the 2p orbitals. So we have all 5 of our atomic orbitals for carbon, but we're really only interested in those last four, the 2s and the 3 2p's. Okay? And then the same thing for oxygen, we get the same kind of output, slightly different energies. And then for the molecule, we have a -19, a -10. So the -19 is the 1s on the oxygen. The -10 is the 1s on the carbon. And then we have all of the molecular orbitals listed. So let's plot these out. This is all of the orbitals, including the 1s's. And now you can see why we don't include the 1s's in our molecular orbital diagrams. Because here's the 1s on oxygen. Here's the 1s on carbon. And here are all the valence orbitals. So that's nice to just do an accurate calculation in Gaussian so you can really see that, yeah, the 1s orbitals are there and they're occupied, but they're so low and so close to the nucleus that they don't interact in bonding. Okay. And so then we zoom in up here where the real interactions take place. And so this is the top part of this diagram. So if you wanted to draw this yourself, you get a new sheet of paper. And so on the left we have carbon, and on the right we have oxygen. And so we have the 2s orbitals, the 2s orbital for carbon, and then we draw them as degenerate, 3 degenerate 2p orbitals, but Gaussian's actually calculating them, and the ones that have electrons in them are lower in energy than the one that doesn't. And so that's why it split the Z off by itself. I wouldn't worry about that if I was just drawing it by hand, right? But Gaussian's giving me the actual energies of those. So I would draw 3 lines with 2p, but you see the 2px and the 2py and the 2pz are different in this situation because Gaussian's trying to be as accurate as possible. So that's the atomic orbitals for carbon. And then over here are the atomic orbitals for oxygen. Notice the p's are pretty well right across from each other. They're slightly off, slightly different. Which ones are lower? Well, the one with the more protons. And so we kind of see a trend here. Fluorine's orbitals were lower in energy because fluorine had more protons than hydrogen. And here oxygen's energy levels, the frontier energy levels, that's a good word for you to know, the frontier energy levels, those highest atomic orbital energy levels, are a little bit lower for the element that has more protons. So think about that. The element that has more protons, those energy levels are lower, slightly lower. So these are the 2p orbitals on the oxygen and the 2s orbital on the oxygen. I've color-coded them with symmetry, and here's the C infinity V character table. The E1 orbitals are green, and the A1 orbitals are blue. Now this gets really busy really fast because we interact all of the same symmetries. So the green symmetries interact with the green and the blue interact with the blue. I think I'll do the blue first. So here's all of the blue interactions. It looks more ugly than it really is. It's 4 atomic orbitals, and 4 atomic orbitals make 4 molecular orbitals. So we're going to have 4 orbitals, one really low in energy, one really high in energy, and 2 intermediate. And although they're not equally spaced, you could if you wanted to. Okay? So if you're just drawing this by hand, 4 atomic orbitals come in, 4 molecular orbitals, 4 lines in the middle. Those have the same symmetry. Questions as I go, they're totally appropriate. If I bump over something, you're like, wait a minute, say that again, raise your hand. Okay, now let's interact the green ones. Well, no, those are sigma. So sigma, sigma star, sigma, sigma star. So these are going to be the 2 s orbitals in phase and out of phase, and then the 2 pz orbitals in phase and out of phase. So we'll look at pictures of these in a second. Then we interact with the green. Oh, we could put electrons into them. Let's do the green interactions now. So the E2 orbitals, so the px and py come together side to side in phase or out of phase, bonding and antibonding. So we have the pi and pi star. And so it looks like carbon and oxygen are kind of showing some sp mixing because we have this sigma above the pi, like we have in nitrogen and all the smaller elements. And so we've got, let's go ahead and calculate the bond order now. We've got all the electrons in there. And so how many bonding electrons do we have? So let's find the bonding electrons. So here's some. BE, and then these three are BE. So the number of bonding electrons minus the antibonding electrons, A, B, E. Yep. Okay, so bond order looks like it's going to be 2, 4, 6, so 8 minus 2 over 2. So 6 over 2 is 3. So it looks like this would give us a triple bond for carbon monoxide. And so one addition to our Lewis dot structures is to talk about formal charge, right? And so we have the octet rule, which is over here on the right. This would give us 8 electrons for everything, but notice how there's a separation of charges. This formal charge would give us a +1 if we calculated the formal charge of this type of oxygen. It comes in with 6 valence electrons. And how many does it get to claim? So this is formal charge is kind of calculated as if these elements went their own way, and the judge didn't care who was electronegative and who was not. The judge just said, all right, for every bond, you split it equally. Right? You take 1 electron, you take 1. And so you take oxygen, it comes in with 6 valence electrons when it bonds with oxygen, with carbon. But then if we were to split these apart and calculate the formal charge, it can only claim 5. It's got the 2 lone pair here, so 1, 2, and then 1 for each bond, 3, 4, 5. So it came in with 6, and it only gets to claim 5. Okay, so 6 minus 5 is a +1. And so that's its formal charge. The valence electrons minus the ones it can claim. So it has a +1 charge. Whereas carbon came in with 4 valence electrons, and it can claim 5. And so it has a -1 charge. It's sort of got an electron in the deal. So that's formal charge. So if you were to reduce the formal charge, you would actually put one of those bonds back on the oxygen. And so this has formal charge of 0. Oxygen comes in with 6 and it claims 6. Carbon comes in with 4 and can claim 4. Okay. So if you were to say, draw me the Lewis dot structure and minimize the formal charges, this would be the structure of carbon monoxide. Okay. If you were to say, adhere to the octet rule, no matter what, then this would be the structure. So which one is it for carbon monoxide? Well, the molecular orbital diagram gives us a bond order of 3. So that kind of favors this one. You see? That's nice. It does kind of favor a little bit of a split in the charges. So which direction does the dipole moment point? Okay. In this case, you've got a positive end and a negative end, so the dipole moment should point to the left. But on the formal charge molecule, most of those electrons are on the oxygen. We know oxygen's more electronegative. It's probably going to pull electrons from the carbon, and so the dipole moment would look this way. Okay. But we do the Gaussian calculation, and it tells us the partial charges on oxygen and on carbon. So we could dig through the Gaussian file and see that the oxygen is slightly negative. So now this is crazy, because what does the MO diagram tell us? Well, it tells us that we have a triple bond, but then it also tells us that the dipole moment is pointing towards the oxygen. So it's really, does this mean that the formal charge is kind of odd, kind of messed up? Yeah, the formal charge is not a great way to come up with partial charges. Okay, but it is a method for, determining different bonding arrangements using local bond theory. Okay, so this is the molecular orbital diagram. It does confirm we've got some triple bond character, and this calculation shows us the dipole moment likely points towards the oxygen. And so then these are the pictures for those molecular orbitals. And all of their symmetries, okay? Now, okay, as far as, this piece being really large and the small sort of p orbitals on oxygen and so on, ignoring those finer details, I want you to stare at every one of these pictures and tell yourself or tell me if you think you could draw it or not. Like if you were making this MO diagram in your notes and I said draw whatever, pick an orbital and draw it, or draw 5 of these orbitals. Could you draw these orbitals? I see some shakes of the head.
E1 pi and
Yeah.
pi star.
So I'm kind of telling you, I want y'all to study these pictures so that you can see what's going on in bonding. Now, let's just look at them real quick. I'm going to sit down and y'all just focus on the screen. This, aside from this sort of being lopsided on the oxygen and lopsided on the carbon, this one, if you just think of this one, this is the 2s orbitals all in phase. And so just drawing that blob that goes over both elements, that's totally legit for an in-phase sigma bond. Okay, so the 2s orbitals are in phase. You've got a blob that goes over the whole molecule. Whereas this one, you have a node in the middle. It's just that Gaussian's not really putting that node right on the bond. It's putting it a little bit more towards the oxygen. But again, ignore the finer points of what Gaussian's doing. And can you draw a red side and a green side with a node in the middle? Yes. Then you got that one right. Okay. Now let's look at the p interactions. So notice that this is a pz orbital on the oxygen interacting with a pz orbital on the carbon. So you could draw it like this. And you could put your little plus sign in there and a minus sign in the middle and a plus sign on that. Where your oxygen is here and your carbon is here. That's kind of hard to draw with this tiny little pen. But that's an acceptable picture. It's a little messy, but, or if you wanted to shade it, you could shade, this side.
Keep one A.
Yeah, and shade this side. The point is, I want to see a node on the oxygen and a node on the carbon and bonding in the middle. So that's a sigma bond with the pz orbitals. And up here we have 2 pz orbitals out of phase. And so if I had the carbon here and the oxygen here, I'd have an orbital like this that was shaded right there, and an orbital like this that was shaded here. So now you can see that node in the middle. So that's an antibonding orbital of the pz orbitals. Can you draw those pictures? Yeah. So you can see that the little crude picture that I've drawn it's compatible with what Gaussian's calculating. And then these over here, you see this is the pi bonding, so the p x on the oxygen and the carbon are bonding together. And so if you were to draw this, here's a carbon, here's an oxygen, bond in the middle, and shade one side, and then shade the same side for this one. Okay, full credit. All right, you're showing that those, and if you wanted to, like say these overlap, you could do this. So you're just showing that the shaded sides are on the same side, and that's going to bond side on. So you can draw these pictures. This one here is just the same picture, but now they're out of phase with each other. You have the carbon, you have the oxygen, shaded up here, and shaded down here. And so now there's a node in the middle. And so that's the pi star, the antibonding. Last little bits of information. These two things right here are incredibly important for inorganic chemistry. Specifically carbon monoxide. It's one of the best ligands we have for getting a metal to go into organic solvents. Okay, you can take a cation, put carbon monoxide around it, and make it compatible with an organic solvent and do organometallic chemistry. Okay, and so this guy comes and bonds to that cation, and then this guy interacts with the d orbitals on the metal. It's called sigma donation with pi back bonding, very important in advanced inorganics. So that's a course that many of you are going to take next, or maybe next semester or maybe next year, but this is really important. So you're going to revisit MO diagrams in that course. It's very important to know about the molecular orbital diagram. And here's what's going on. This carbon monoxide brings that orbital in, and then the d orbitals on the metal back bond to the antibonding orbital on the carbon monoxide. We'll look at ethene next.